Okay, I'm very excited to talk about the Voss-Weyl formula. I have it written right here. I'll talk about its significance in just a moment. First, I want to mention the two names that are part of the name of the formula. So, of course, Hermann Weyl was a preeminent geometer of the 20th century, very famous German geometer, maybe Swiss, I think German. He came to the United States, escaped from the Nazis, came to the United States, spent 20 very productive years or so in the United States with great contributions. He was a wonderful author. He wrote a book on relativity called Space-Time Matter. That was a great inspiration for me when I read it. Every word in that book is given a lot of thought, and he wrote it with a great sense of responsibility. And he felt that he was a messenger of the mathematical aspects of geometry and relativity to the broader public. And I think his book accomplished that. It's now available under Dover, and of course I recommend buying it and reading it. And it'll be much easier to read after you study these lectures. So that's Hermann Weyl. Voss, I didn't know who Voss was. And I had to do some research on the internet, and I was very happy to discover that he's actually still living, and he lives in Switzerland, Konrad Voss. And I met with him 2 years ago. I visited him in Switzerland, and he's a wonderful mathematician. We had a long mathematical discussion, still extremely active, wonderful mathematician, very interesting, and also a great human being. So, and it was very nice for me to meet someone whose name was attached to a very important and very elegant formula. He, of course, didn't know that the formula was named after him. So in the middle of our dinner, my original email to him said, "Hey, there's a formula named after you. I'd like to meet you and learn about the history of the subject." I learned a lot about the history of the subject from him. But he, of course, didn't know that the formula was named after him. It's really only in Russian literature that this formula has this name. In American literature, I don't think it has a name. So because I'm Russian, I carry on the tradition of calling this formula the Voss-Weyl formula. And in the middle of the dinner, he asked me, "So what's that formula that's named after him?" And I said, "This one." And he said, "Well, that's so simple, it shouldn't have anybody's name." Maybe he's right, but I think it's actually the ultimate tribute to someone's accomplishment when something very simple is named after him. So he certainly deserves to have his name attached to this formula, if anybody does. Okay, so that's the story, and that's why I'm particularly happy to have a chance to talk about it. So let's talk about the significance of this formula. This formula, of course, is an alternative expression for the divergence. The divergence is an invariant combination. That's very obvious from here. That was the whole point of developing the covariant derivative and so forth, so that when a covariant derivative is applied to a tensor, the result is a tensor of order 2, in this case with one covariant and one contravariant component. So when they're contracted, we're left with an invariant. So we get meaningfulness, geometric and physical, for free with tensor notation. On the right-hand side, there are non-tensors all over the place. This is not a tensor, this is not a tensor operation, and of course this is not a tensor operation. So what's the advantage of that formula? The advantage of this formula is that you can use more primary concepts to evaluate the divergence. In particular, you don't need the computation of the Christoffel symbols. There is nothing particularly difficult about calculating the Christoffel symbols, especially in our day and age of computer algebra systems. But it's nice to be able to skip that step. And actually, the expressions that you obtain from this formula end up having much more structure and much more aesthetic appeal than expressions obtained by this formula, as you'll see. If you look up the Laplacian of a function, of course, the divergence is only half a step away from the Laplacian. So if you look up the Laplacian or the divergence in spherical coordinates, you can kind of see the signature of that formula in the way the terms are grouped in the answer. Okay, so that's a very important formula. So right now, I'll show its derivation. And using this formula to evaluate divergences and Laplacians of general functions in various coordinate systems, I'll save for a later time. I think we'll have a few lectures devoted to applications. This is more theory and derivations and the structure of the subject, and then we'll actually use this wonderful subject, which I don't think I do enough of. Okay, so in these lectures. Okay, so to prove this formula, let's see the ingredients that we'll need. When you apply the product rule to this product, we will need to evaluate the partial derivative of the square root of the metric tensor. Of course, that will require the partial derivative of the determinant of the metric tensor. I forgot to say determinant. Of the determinant of the metric tensor. And the way we'll approach that exercise is by first thinking of z as a function of its 9 entries in 3 dimensions. So it's a composite function that depends on its 9 entries, where each entry depends on the spatial coordinates. So that's how we'll treat it. We'll treat it as that kind of composite function. So that derivative will be the derivative of the determinant with respect to one of its entries times the derivative of one of its entries with respect to the spatial coordinate. So let's first arm ourselves with that formula. I think we've derived it before, but might as well derive it again. So here's what we'll need. We'll need dzi of zjk, an entry. In this case, I'm thinking of it as an entry of the covariant. I always think of it as the entry of the covariant metric tensor. So there you go. Okay, so in Euclidean spaces, this is a particularly easy exercise because the entry of the metric tensor can be written as a dot product of the corresponding basis elements. Next step is, of course, the product rule. Well, let's combine 2 steps into one, because the product rule is an easy step. We'll have z dzj dzi, which, of course, invites the Christoffel symbol. So it will be gamma ij, the order of the lower indices doesn't matter, m z m, and then dotted with zk. That's the first combined term of the product rule, plus zj dotted with the derivative of this covariant basis with respect to zi. So it'll be gamma ik m I k z m. Okay, now I think we can combine the next 2 steps into one. Let's see what we'll have here. This, of course, is the metric tensor with indices m and k, and we'll then invoke the index juggling convention applied to the Christoffel symbol. M will be lowered and will become k, which is written this way: gamma k, comma ij, plus similarly gamma j ik, j I k. Very nice formula. Clearly symmetric in j and k, because if j and k were to trade places, this term will become this one, and this term will become this one. So a very, very nice formula, and of course, we've seen it before. Okay, so let's put it in the bank, and of course it will become needed in the next step, where we'll figure out the derivative of the metric tensor with respect to the spatial coordinate. How does the metric tensor change from one point to the next? What is the rate of change? This is the answer. And as I described, we will treat this as a composite function of its entries being zjk, And each of the entries, of course, depends on the spatial variable, and we know the answer to that derivative. So the chain rule looks like this. dz jk, that's the derivative with respect to each one of its entries, times dz jk dzi, and of course the Einstein notation is wonderfully invoked in this relationship. So this is a double summation over j and k. So the tensor notation is perfect for this kind of calculation. Okay, so the answer to this determinant, this derivative, you can find in the lecture on determinants and cofactors. At the very end, we derive this and we show that it equals the determinant itself times the inverse of the matrix, which of course is the contravariant metric tensor. So very nice. And this we have over there. This equals gamma k comma ij plus gamma j ik. And I just want to remind you that it's our convention. Conventions vary from textbook to textbook. Which of these three indices is first, second, and third? So according to the convention that I use, the upper index is first, and the lower two are second and third. Some books use the opposite convention, where this is first, second, and this is third. But in Weyl's book on space-time matter, that's the convention it's the convention that I used that was used. So I borrowed it from there, and I'm happy with it. Okay, but let's see what will happen here. So now it will actually in a moment not matter because the index is getting raised back up. So you see what happens here? It becomes gamma j ij. And this will become gamma k ik. Isn't that great? So let's actually do this kind of analysis in our heads. Because number one thing to realize, because the j index here and the k index here, the index k here are dummy indices. They're dummy indices. So these two terms are the same. So we'll have z twice, 2 times z gamma. And I will actually write it as j I. What I also did was switch these two indices, and of course this object is symmetric in these two indices, so it's valid. So here's the answer. Very, very appealing answer. Okay, so now we're ready to analyze the derivative of the square root of z. So that will still fit. The derivative, and then we're pretty much ready to go to derive the Voss-Weyl formula. dzi equals 1 over square root of z. Excuse me, 1 over twice square root of z times dzi, which we're of course derived right here, and that's the answer. So it's times 2z gamma ji. That's great. The 2's cancel, square root of z's combined, so we have the answer is square root of z times gamma ji. All right, now we're in perfect position to derive the Voss-Weyl formula. And I just realized that the microphone was unplugged the entire time, so I'm hoping that this lecture is coming out fine in terms of audio. So I will pause right now, plug in the mic, we'll see if there's any difference, erase the board, and derive the Voss-Weyl formula. Okay, let's derive the Voss-Weyl theorem. Let's start on the left-hand side and express both sides of the expression in terms of the Christoffel symbols. You know there are Christoffel symbols in this expression, and we just saw that, of course, there are Christoffel symbols in this expression as well. And they end up being a perfect match. So on the left-hand side, we have the divergence of Fi, which, let's remember the definition, is, of course, the partial derivative of Fi with respect to dzi. So half a step back. So this here represents two operations, consecutive. First, take the covariant derivative, and then do the contraction. So maybe the covariant derivative will be sub j, and then we contract on the two available indices. So we're going to do both of those steps together. That's why I have d of I dzi plus gamma I upper, I lower, that's the contraction, times m, for lack of a better letter. I think it'll be a different letter when we do the right-hand side, times fm. That's great. We're done with the left-hand side. So compact that it makes you wonder, did we really need a formula, an alternative formula? And the answer is yes, it's nice to not have to compute the Christoffel symbols. It was especially nice before when there were not computer algebra systems. All right, on the right-hand side. On the right-hand side. Let's use the product rule. We'll have 1 over square root of z times d square root of z dzi. This multiplies fi. Plus, all right, now d dzi will apply to fi, and the square root of z will just cancel this square root of z. So it'll just be d fi dzi. So you can almost already see that the two expressions are the same. Very neat. Okay, and with this term we know that this derivative, I'm just trying to remember it from just a moment ago, so is actually square root of z times gamma, how did we write it? J I f I plus dfi dzi. And I don't think I need to go any further because you see that these two terms cancel. And do we have a perfect match? Yes, we do. Just requires one act of index renaming. So there we go. That's the simple derivation of the Voss-Weyl formula. Of course, this was the fun part of the derivation. It was in deriving this formula that everything worked out so nicely to give such a nice, albeit non-tensorial answer. So just one last thing that I mentioned, the way this formula is actually used. It's used more often for the Laplacian, the divergence, at least in my career. So let's just give an equivalent expression for the Laplacian. So Laplacian is the sort of thing that's applied to an invariant, at least a scalar. And interpreting that expression, we have 1 over square root of z d zi of square root of z. Now let's pause for just a moment and realize that it is the divergence of this. And we want to express everything in terms of partial derivatives. So of course this, in terms of partial derivatives, is zij df dzj. So that's what the Voss-Weyl formula looks like for the evaluation of the Laplacian. So there you go, the Voss-Weyl formula. We're almost at the surfaces. I think over the next couple of lectures, we'll dot a few of the I's of the things we missed in the past, prepare ourselves for the surfaces, perhaps by talking about linear algebra in tensor terms. I'll think about what order to do the lectures in, but we're almost at the surfaces, and Gauss is remarkable theorem, which will be one of the highlights of this entire sequence. Thank you very much, and see you next time.